All right. What we're going to do is just do some quick review for the exam. So your questions will deal with one of these two things, either the relationships that we talked about with depth and water or the Maxwell-Boltzmann distribution. Your question is actually a 20-point question, and so you'll have 2 less questions than the other people. Well, 2 less. You'll have 8 questions in common with people in Physics 151, and then 1 question that's worth 20 points. The reason I had it 20 points is because I have you calculate it 2 ways, and I figured that made it, at least conceivably, twice as much credit. So, the topics it could be, with liquid we had 3 topics, 3 things that we dealt with. One was how the pressure changes with depth. Now, the example I did, we had a constant density rho, but you don't have to have a constant density rho, and in fact, density usually isn't constant. As you go to greater depth, you have higher pressure. But because you have a higher pressure, that's going to cause the fluid to compress a little. And so I could give you something that has you calculate the pressure as the depth increases, and you may or may not have a constant density. If the density is not constant, you would have how the density changes with pressure. You could then have the one calculating the force that's placed on a surface. You have the force that's placed on a surface. It's pressure d area, and you have to integrate over the area of the surface. Now remember, the way we did that in class is we said, okay, we have d area, but the pressure is the same at the same elevation. So I made my area the width, all the same elevation, times some dx change in height. And so then I had my pressure was a function of height, and my variable was height, and the width was constant. So this dA became the width times, and I'll call it dy here for the height. And so while it is a dA, it's a integral over area, you can immediately, just in your head, if you will, do the integral over one of those 2 dimensions and come down to that. And then we had the torque option, calculating the torque due to the force. And so you put this dF into that equation. D torque is R cross dF. And in the situation we worked out in class, we had a fixed angle between R and F. Remember, a cross product, what is a cross product doing? She's exactly right. Multiplying the perpendicular parts. But in our problem that we did with the dam, we had the R was a vertical distance, and the force was a horizontal force, and so they were always perpendicular, so the magnitude was always R times dF. And furthermore, the direction was always the same. And so we could make it a simple problem, not one that has to have a cross product, except for we had this additional depth term in there. That's what made the calculation different. Any questions about the liquid parts that we might have on the test? All right then, let's move to the next one, the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution, obviously you don't have to memorize this equation. That would be asking a little much. But you need to be able to find things from it. So you need to be able to find the sum of the probabilities. What should the sum of the probabilities be? It should be 1. If I give you all the options for rolling a 6-sided die, you add them all up, they better come up to 1. That is, when you roll the die, you're going to get some answer. Same thing here, except for instead of rolling a die, we're talking about, well, what's the speed going to be for an atom in a collection of billions times billions of atoms. Well, let's go with billions times millions. It's somewhere between those two numbers for our typical situation. And so then the probability is the probability that a specific atom will have these different speeds. And if you say, what's the probability of having exactly this speed? Well, the probability of having exactly this speed is 0, always. The actual probability, this is a probability distribution, but the probability is equal to, that's probability of speed between v and v plus dv. Right, this function has to be used in this fashion if you're going to find something about probabilities. Probability being between speeds v and v plus dv is not 0. And that we can get from this number, or from this function. And so some probabilities, how did you find the sum of the probabilities? You integrated from all ranges of possible speeds, which we approximated with the non-relativistic equation to be from 0 to infinity. I think it was you that pointed out, well, really, it can't go up to infinity now, can it? Okay, how about the most likely speed? Okay, so the most likely, you can look there and get an idea of where it should be, because it's at the maximum. How do you find the maximum of a curve? Okay, find critical point, which means you take the derivative set to 0. Now remember, when we did this, we found 3 different values that came to 0. How do we know which one it was?
Second derivative test.
Okay, second derivative test, or logic test. The second derivative test, you take the second derivative is positive, then it must be a minimum. If the second derivative is negative, it must be a maximum. If the second derivative is 0, then, inflection point. Or logic was that, well, the maximum can't be at 0 and it can't be at infinity just based on what we see in the distribution. But a lot of times we like to see the hard, cold, the math is unforgiving. Whereas there's fuzzy thinking when you're all, well, I can look at the graph and I see the peak. Average speed. How do we find the average speed? I like to back up on this. How do we find the average position for mass, what we call the center of mass? Okay, the integral of x dm over the total mass. Well, when you think about this, the dm, the dm over total mass, my logic here isn't going to work out, but you have a weighting factor for each position, and then you add up the weighting factor times the position, and then you divide by the total. So the dm over the total mass is the weighting factor, it's the probability. And then you did the integral over all the probabilities to get the center of mass. If I find the average of a test, I do the same thing basically. I take, one way of doing it is to take each individual score and add them up and divide by the total number of tests. Another one is to say, well, I have 7 people that got, 100 out of 100, and I have 5 people that got 94 out of 100, and I take those probabilities, 10 over 100, whatever, and then I can take the probability, multiply by each score, and add them up. That's what we're doing here. So we're taking the probability, multiplying it by, it's not a score, it's not a mass. What are we using here? We're finding the average speed. So we take the probability of each speed, multiply it by the speed. Well, the probability of the speed is this thing here. multiply that by the speed, and then add them all up. And of course, if it's a continuous function, what does add them all up translate to? Integrate. So for this here, to find the most likely speed, the average speed, we did the integral of v f of v dv. The sum of probabilities was the integral of f of v dv, and that had to be 1. How do we find integrals like those two integrals? Yeah, I gave you that little cheat sheet because you're not going to do it otherwise. Yeah. Otherwise you're going to be often, this should have been 200 points out of 100. Right, because those are not integrals that anyone just does in their head. Okay, so the average speed was integral of v f of v dv. And what was the RMS speed? Okay, we have to take the square root. Remember, RMS, we had on Flip Friday what RMS means. Root means squared. And so the first thing we did was we square the velocity and find the mean. Well, square the velocity. And then to find the mean, I have to multiply by f of v dv and integrate over everything. And then what was the other part of RMS? Root. Now, of course, I do it in multiple steps with my math. I don't write it as an equation like this when I do my math. But I do that integral, and of course, our range of speeds is 0 to infinity. And so I do that integral. So, the things we have for the test this afternoon are going to be between this menu of items, the stuff we had here and the stuff we had here. So that was a nice, let's say 15 minutes, because I believe I did start about 3 minutes late. Wait, that would be 15-minute review. So now what questions do you have for me? Do I have any what?
Any questions, problems,
Ask me, give me something specific and I will make something up on the fly. What would you like to do an example of, Tosan?
the one about finding pressure.
Okay, so let's just let us say that density is not constant. That's, I think, what you're saying. Let's say density is equal to something like this, saying that density is going to decrease as you move away from the center. Has some density rho 0 at the center and then decreases as you go away. And then ask, what would the pressure be as a function of distance away from the center? That actually wouldn't be a good problem. I can't do that one. The reason why is reasonably simple. The problem I gave, even though this is an exponentially decreasing function, you still would have enormous weight above, and I would be, well, I would have to find my my pressure. I'll show you why it's a bad idea, what I just wrote. dP is equal to rho g. In this case, it'd be dr. First of all, I was defining it for a sphere. And for a sphere, I actually have to put in here the area part of 4 pi r squared dr. That's the first part that would be a change. I think that's where I put it. And then I would have to do my integral from infinity down to the height I want. That's the upper limit would be infinity and the lower limit would be height I want. It would be a bad choice. I'm not going to give you something that's a bad choice. I was thinking of other things that I have done, like, find the mass of the Earth, but that's not using this equation. So let's try a different one. Let's say the density question?
So when is it important to know if it's compressible or incompressible?
Well, for this here, if density is not constant, then for this equation, it's going to be not constant, probably because you compressed it. But I just give you an equation rather than having you try to figure out how the density is changing. Right. And so all you're doing is, you're not focusing on the compressibility aspect at all. You're focusing on being able to use this. So let's just say that I gave you, instead of that the density is equal to this times 1 plus, okay, it's got to increase as we go down. Well, let's just say 1 plus y squared. Right, so the density is going to, I got to put a factor here. By squared, otherwise my density gets really huge really quick. So b is going to be a factor for how quickly the density is changing. Now we have density that's non-constant, and I can find the pressure as a function of depth. So this side has only pressure on it. This side has only y on it. So since I need to have the same variables. I'm sorry, I'm making stuff up on the fly and not hitting everything perfectly. So this side has only x on it, this side has only pressure on it. Because we have our variables separated, what can we do next? We can integrate. So I integrate each side independently from pressure initial to pressure final, and from x initial to x final. And then I just do my integral, so I would have P final minus P initial is equal to rho aught times and at this point I put in my limits for the x. Notice I didn't want to make a big mess. Put in my limits for x, and I have an equation for the difference in pressure between starting and ending points. Yeah?
And we would consider pressure final to be the bottom, correct?
Yes.
Okay. So then our pressure initial, if we were saying going all the way up to the top of the surface, then our pressure initial would just be atmospheric pressure, correct?
Yeah, like say we're doing a real problem, like, we're talking about having molten magma, and at the Earth's surface, the pressure would be atmospheric pressure. So that is indeed what you'd start with for pressure initial. And so I would set up my problem. If it was molten magma, here's the Earth, and we're treating the Earth as, at this point, oh, come on. Treating the Earth just as flat. And so then I would be measuring my x down this way. And so I would set my x initial equals 0, assuming I start at the surface. And pressure initial is equal to 1 atmosphere. And then I would have my pressure final somewhere down here at x final. So that's an example problem, Sasan.
Can we do an example?
What was it you wanted, Tori?
Oh, I was basically going to ask for something that he did.
Okay. Okay, another example. What other, Ryan?
I guess maybe this is a side note, but I'm a little nervous because I'm not seeing how we would come up with these in multiple approaches. You mentioned that on the exam we were going to be asked to calculate these in 2 different approaches, and maybe I shouldn't pry into that.
Well, I said 2 different calculations.
Different calculations. Okay. I guess that'll be obvious when the time comes.
I believe so.
Because I'm like, it just seems like these are not very straightforward, but they're like, this is how you do it. This is how you do it.
Yeah.
Oh, the Maxwell-Boltzmann, whatever. The sum of probability gave us probability is FMV dV.
Mm-hmm. Yeah, the probability distribution is the name for that. And then the probability of, I mixed colors. Let me unmix the colors as best I can. Okay, they're well, almost right. The probability of speed between v and v plus dv is the distribution times dv. Right, so this here that's underlined is the actual probability. The f of v is the probability distribution.
And that's FV.
Yeah. So the difference in terms, I mean, the terms probably don't really mean any different to you, right? But it's important that we know how to find the probability. The probability is this function times a small width dv, and that's the probability of being within that width dv. Yeah, go ahead.
So, on the force of the dam caused by water, or forces on dam caused by water.
Yeah.
I just had the P is pressure.
Mm-hmm.
That dA. Can you run through like finding the dA real fast?
Okay, so we have a dam. If we look at the side view of the dam, we see something that looks like this. And we have, as we go down, okay, so here's the water level. As we go down, pressure increases, right? And so I set my coordinate system so I have x equals 0 at the surface, and x is increasing as we go down. And I'm going to then define, some little width or change in height, dx, along that dam. Now that's looking at from a side view. Now if we change, instead of looking from a side view, we look from a front view, then the dam is just this big, of course, monolith. And I still define my x as going down like this, but now my dx is still this change between those, and I have the width w across. And so if I have a rectangle, I can find the area of the rectangle by multiplying the height by the width. And so I have the end result, dA, the small amount of area upon which I have constant pressure P, is equal to that width times dx. Now as x changes, the pressure changes. But it didn't change as I went along the horizontal, so that's why I could take that whole horizontal swath and combine it.
Okay, so we could rewrite it as like P with dx.
Yeah, like I did here. I didn't write the P part, I just did I did the dA part. Sure.
So will those starting equations be on our equation
Yeah,
list?
yeah. I haven't gone through and checked the equation sheet yet. That's my next step. That's where I was about to start when I looked at the clock and saw that class was starting.
Okay.
I got the test all written, though. It's just the equation sheet that's not ready.
Yeah.
Yeah, that's what I'm thinking.
When you have the dx equals a PDA, to get that P, we have to integrate the top thing, right?
It depends on the situation.
Unless you give it to it. Okay.
Yeah.
And then, okay.
Michael.
Oh, you can see an example of the torque about top and bottom.
Sure.
We have time.
You guys don't see Michael's face when he raises his hand, but he gets this little chagrined smile when he raises his hand. Yeah. So let's just add a page here. And let us suppose that I have my dam. So drawing a side view of the dam again. Okay, I'm going to use straight line tool because I am wandering about. So there's the dam face, and I'm going to make it have a straight backside just so it's, looking nice. Okay, got my dam. Going to put a water level on here. There's the water level. Now let's suppose that I gave you this problem and said that the water is incompressible, so pressure, well, let's just start. Water is constant density rho. Now you already have an equation that will be given that says if it's constant density, pressure is equal to rho g x. Now technically that's pressure difference, right? Technically it's this. Delta P is rho gx. And so pressure is going to be equal to the pressure at the top plus rho gx is what you get from that. If I said integrate to find the pressure, then you would have had to start by saying, okay, dP is equal to rho g dx. Integrate both sides. And I would have had P final minus P atmosphere is equal to rho g x final. Same equation, right? So if I asked you to do it through calculus, it's only one line to do that. Yeah.
And if instead of going up at the top, we were for some reason just going like halfway up or something, then that second term wouldn't drop off, right?
Say that again.
If for some reason instead of going all the way up to the surface, if it was like what's the pressure difference from say the middle of the pool down to the very bottom,
Yeah.
then instead of having the pressure of atmosphere, we'd have
Pressure wherever you started.
Instead of having the second half of that rho gx, top off would be rho gx.
Yeah. Okay, now I'm going to find, to make my life simple, I'm going to find the torque about this point here because then my R is going to be equal to X. So if I find the torque about A, actually, no, let's do it about B. B is harder. If you can do B, you can do A. Let's find the torque about B. So to find the torque about B, torque is R cross F, right? Or d torque is equal to R cross dF. So now what is my dF? What would dF be? Yeah. And I have a direction to this that has to be, in the right direction. I'm just going to put F hat here for the direction, right? Because we know what direction is going to be in my picture, but it gets a little bit confusing when you just try to throw it up there and you have a cross product you have to have a vector on both sides of a cross product. You can't have a vector on one, the scalar on the other. Okay, so I have that. So now I look at my specific situation and I say, okay, if I'm going to find the torque about point B, then my R is going to be going up like that, right? But when I was looking up here at the pressure function was coming down from the top. And so I need to make sure I define things carefully. So I could say, for instance, let x equal height minus r. So that is, when r is 0, then your x is the height of the dam. But as r gets bigger, your x is dropping. Why do I do that? Because, looking at my picture, if r is 0, the depth is the height of the dam. And as r goes up, you have a smaller distance. So now that I've made that switch in variable, then I can say, and now I'm dropping off the vector sign. Why? Because my R is vertical. What direction is my force? Into the dam. And so I have, those are perpendicular directions. R cross F, using the right hand rule, I'm going to get that my torque is into the screen the way I've drawn it. Right, because I use fingers first in the direction of R, and then orient the hand so I can bend them in the direction of the DF. Thumb goes in. So I have my direction taken care of. Because they're perpendicular, the magnitude is just going to be equals R times my pressure, which is and then I have to have my dA, which is W dR, because I have my dR, the little piece right there. So that's my full-on equation, which I would like to multiply out to make it look simpler. There I've separated it out to 3 terms. Obviously 2 of them are integrals of r dr, and the third one is the integral of r squared dr. And now I can just integrate from 0 to h. I'm going to combine these 2 back. And doing this, then I will have my final answer. And so there's my final answer. And of course, 1/2 minus 1/3 is 1/6. And as a final thing, that's the torque created by the water. There's also going to be a torque created by air on the back side. And the torque created by air on the back side will exactly cancel this. So this part here is going to be canceled by the air on the back side of the dam. And so the net torque is just going to be the second term, the 1/6 rho g width times height cubed. So that's an example of
Say
that.
last part one more time.
What was that?
Say that last part one more time. This is the front part of that.
This is the torque that's caused by the water on the front part of the dam, right? So if I just ask what's the torque caused by the water in the front part of the dam, the full thing's the correct answer. But
That's all the torque.
you had the air pressure that was also applying forces on this side. And that air pressure is going to create a counter torque that is exactly equal to this term that I put a box around. And so the net torque that is on that dam due to the water, that is if you take away what the air is doing on both sides of the dam, is just the second term. And of course, I would try to give you words to make sure it's clear what I'm looking for, rather than saying, well, it could be this or this, depending on which one you wanted. Yes?
And if we're doing it about point A instead of point B, then we would just have x equals r, right?
Yeah. Yeah, so I would have just done x is equal to r and done my integral downward instead of upward.
And then instead of having h's, you would have x, or would you just say,
Instead of what?
instead of having h's, you would have x? Or,
Well, I would have done my integral from 0 to h going down then. And so it would have been ever so slightly simpler because I wouldn't have had this. Next question. All right, well, that's what I got. If you're satisfied, you can
can I ask a
come back in
non-question?
2 hours. Yeah, you can.
Okay, so on the chapter 14 practice problems that you had posted,
Mm-hmm.
there was one that was talking about basically you have a concrete wall with that's this thick, and then there's a layer of wood.
Oh yeah,
that's this
did
thick.
that this morning because it was fun.
What's the effective convection of thermal conductivity? How do we do those types of things?
Okay, let's just draw out our picture. So I have a concrete wall. Yeah, I want to make it a solid concrete wall for some reason. I have a concrete wall, and then beside that concrete wall, I'm going to have a wooden board. So I have something like that. And they give you information about, I'm going to say LW equals the length of, or the thickness of the wood. Excellent. Which was 2.50 centimeters in that problem. And then this here I'll call LC for the length of concrete. Well, thickness once again is what I'm and that was equal to 15.0 centimeters. And then they give us the concrete has a
0 watts per meter degrees Celsius.
what's the number?
1.70.
And yeah, I'll just put the same as they did. And of course, the wood they also give us
Was 0.0407. Yeah, that.
I remembered that one. Once you said the 1.7, I remember both numbers. So they gave us those numbers, and then they finally simply ask us, what is K effective? So as I'm going through this, I have to first reason, okay, what is K? What are we talking about here? What are we talking about in this problem?
Basically, how well this thing as a whole will conduct heat.
Okay, we're talking about how well it conducts heat. So we have the equation for heat conduction that says the rate of conduction is equal to K multiplied by the area that it's going through divided by the length it goes across, and then times the temperature difference. Well, let me just put delta T, it's shorter. Now in my problem, what direction is heat flowing?
It will be from inside of the house to outside.
Okay, so my heat must be flowing something like this. And so I'm going to say that I have temperature inside here and temperature outside here. And I have an interface. So I'm going to call the temperature at the interface temperature mid. Since we've defined the direction that it's traveling, we can now identify what is the L in this equation, what is the area in this equation. Now, I already did that because I knew what I was doing when I started. I used L for thickness because that's the distance that the heat has to travel. And the L in that equation is the distance the heat has to travel. A is the area, the cross-sectional area seen. So A would be the area seen by this surface. It gave us its width and its height, right?
What told us the area was 10.0 meters squared.
Oh, okay, so it just told us A is 10.0 meters squared. So we have that number. The fact is it makes no difference to the problem. But they gave it to us, so you could write it down if you wanted. Now the question is, how do I find the effective K? Well, what can you tell me about the rate that heat is flowing out of the inside of the house compared to the rate at which heat is flowing to the outside of the house? The rate that's leaving the inside compared to the rate it's entering the outside.
Simply the inside of both.
It's simpler.
Well, it should depend on the thickness of the material, though, so I should take that into account.
They're the same. The rate that it's going in compared to the rate that's coming out has to be the same. Well, if we're in equilibrium, the wall is not going to be heating up or cooling down. It's just going to have heat flowing through it. Now, if we're not in equilibrium, like if we started with the temperature inside and out were the same, and suddenly the temperature outside went up by 20 degrees Celsius, well, then we're going to have to heat up the wall a little bit on the outside before we have equilibrium reached. But this is presupposing that we reach equilibrium, because we're usually in some quasi-equilibrium state. So we have the power is going to be the same going into this side as leaving this side, which means it has to be the same going through my wood as it is going through the concrete. So I can write three different power equations. The power, of course, is the heat per time. I can write power is equal to K effective, what I'm looking for, multiplied by the area, multiplied by what's the total length that the heat has to go through?
LW plus LC.
Right. LC plus LW, multiplied by the change in temperature, which would be, let's just put temperature in minus temperature out. So I can do that one. Or I can look at just the wood. And I can say the power for the wood, so I'll put here total power for the wood is equal to the K for the wood over the length for the wood times the area times, well, we still have T in on one side, but we have T mid on the other side. And finally, what would I have for the power for the concrete? Yes. So now I have these three powers that we said all equal each other. The total power is equal to the power going through one is equal to the power going through the other. And how many unknowns do I have? Well, T in, T out, K effective, oh, and T mid. Well, that's way too many unknowns, right, for three equations. But it will turn out that the T in and T out shouldn't matter, right? The K effective shouldn't depend on what the temperature inside is compared to the temperature outside. It should only compare on the materials and how thick they are. So I'm not going to count T in and T out as unknowns because it shouldn't matter on that. Now, the T mid is definitely going to vary if I change what the thicknesses are. So the T mid is still a variable. So now if I look at my unknowns, I have T mid and I have the K effective. Getting better. I have two unknowns. I have three equations. I can make two equalities with these and have it done. So what I do is I take the lower two and I combine them. That is, I set power for the wood is equal to power for the concrete and solve for the temperature in the mid. And then solve for K effective. So doing the math, and if anybody wants to leave, feel free to leave. We're past time. Doing the math, I'm going to have, and I don't have enough space, so I'm going to just duplicate this. So I'm going to set these two equal to each other. Okay. What's the first thing I see when I set those equal to each other? I can cancel out the A. Like I said, the A just doesn't matter. I'm sorry, I realized I didn't need to have the other things, and I can bring these closer now. Make it make more sense. So I'm going to cancel out that there A. And then I want to solve for T mid. So I'll bring the T mids over to the right side and the T out to the left side. And that will give me on the left side so T mid is equal to now. I don't love dividing by a fraction, and so I am going to, well, I'll wait. Eventually I'm going to get rid of that dividing by a fraction thing because it's a nuisance. So now I have my T mid, and now I'm going to put that T mid into the equality between, well, let's just do the first two. I'll come up here and copy the first two. It's close. I missed something. Okay, so I set these equal to each other, and now I'm just going to substitute the T mid in there. So if I substitute the T mid, this is equal to now that's pretty big, but let's get a common denominator. To give this a common denominator, I would have, okay, the left side, K effective, right side, okay, now it's nice and long. Right, the reason I did it was because it's fun and to make sure I didn't make mistakes. Let's cancel the A's and subtract. These two here add up to 0. And these here have the same factor multiplied by them. So I can take this and now more efficiently write it. Right, since these were both multiplied by Kc over Lc, I factored the Kc over Lc out. And now again I can see there's some canceling I can do. The T in minus T out cancels. That's good. Like I said, that shouldn't have mattered. So it's good that it canceled out. It doesn't matter. And now I have this, divided by a fraction thing that bugs me. So I'm going to invert and multiply. Invert and multiply. I don't know how you guys feel about this process, but I say that that is the simplest way of combining those fractions so I can invert and multiply. So I invert that and I have K effective over LC plus LW. Obviously I'm going to want to get rid of that in just a moment. Is equal to KW, KC, brought this one to the other side, over LW, LC, brought this one over to the other side. And then with my invert and multiply times LC, LW over KC, LW plus KWLC. And so in my final steps here, we see these now cancel and multiply this across, and I will have that's K. That for my answer. and then you put the numbers in.
I also have a question for the chapter 13 stuff. Did we need to know how to do like the average distance between particles?
Yeah, that's a very simple. It's a very simple physics problem. It has the original thought aspect. If you take an ideal gas, the ideal gas is governed by PV is equal to NKT. And so I can take this and say, V over N is equal to KT over P. Simple enough, right? Well, in this case, if I have one atom, that atom would have a volume that it is filling of this V, right? If I just put N as 1 in that V, that's the volume one atom fills. And so I say, okay, I have a bunch of atoms. Each one is carrying its own space. What's the separation between them? Well, I drew these as circles. I use a spherical volume. This is R, this is R. The separation between them is going to be 2R. And so I say the volume for one atom, V is equal to parentheses 1 times KT over P, and that's equal to 4/3 pi times that radius cubed. So I just solve for radius.
And the distance will just be 2.
Yep.
How about the stuff with mean free patterns of a molecule?
The mean free path, I don't recall us doing that.
Fusion constants?
We did not do that. I had it in the lecture and we didn't get to it.